Hi boys and girls, today we begin the Unit 3 lectures, Differentiation Rules and Applications. In the first part of this unit, we'll be adding to our ability to take derivatives of increasingly more complicated functions by learning the product and quotient rules, the chain rule, implicit differentiation. In the last part of this unit, we will study a couple of applications of the derivative. Today's topic, product and quotient rules and higher order derivatives. And today's lecture will comprise part 1 of that topic. We have learned that it is to our advantage to arrange a function so that we are able to use the power rule whenever we take a derivative. However, depending on the complexity of the function, that is not always possible. So we're going to learn a few more rules which will allow us to advance in our determination to take a derivative of any function we see. The first is the product rule. The product of two differentiable functions, f and g, is itself differentiable. Moreover, the derivative of fg, the product of those two functions, is the first function times the derivative of the second, plus the second function times the derivative of the first. And here you see it mathematically stated as well. The first function times the derivative of the second, plus the second function times the derivative of the first. Let's practice using the product rule. You can see that the function h of x is a product of two functions. We'll label this function f of x, and we'll label this function g of x. For this function, it would be possible to FOIL these two factors and then use the power rule. However, of course, that will not always be the case, and so let's practice using the product rule now for the times where we will not be able to use the power rule. Remember then that the product rule states that the derivative of this function of products will be f of x, the first function, times the derivative of the second, g prime of x, plus the second function, g of x, times the derivative of the first function, f prime of x. So we start with f of x, which is 3x minus 2x squared, no change made to the first function, times the derivative of g of x, which is just 4, plus the second function, 5 plus 4x, times the derivative of the first, which is 3 minus 4x. Now we should do some distributing and foiling and clean this up a little bit. We're going to have h prime of x is equal to 12x minus 8x squared. Over here, when we FOIL these terms, we're going to have plus 15 minus 20x plus 12x minus 16x squared. Combining like terms, we do have two x squared terms, so this gives us negative 24x squared. We have 1, 2, 3 x terms. 24 minus 20 is a positive 4x, and then plus 15. And that is the derivative of h of x. Here's another opportunity to use the product rule, and one involving a trigonometric function. We will let f of x be 3x squared. So this will be f of x. And we'll let g of x be sine x. So first of all, let's recall the product rule. It's going to be f of x, the first function, times g prime of x, the derivative of the second, plus the second function, g of x, times the derivative of the first, f prime of x. So for this function, the derivative will be the first function, 3x squared, times the derivative of the second, and the derivative of sine x is cosine x, plus the second function, sine x, times the derivative of the first function, which will be 6x. Other than moving this to the front of this term, that's it for taking this derivative. These are not like terms, and so there will be no combining of like terms or further simplification. Here we have another opportunity to take a derivative. y equals 2x cosine x minus 2 sine x. In this first term, we have a product. We'll let 2x be f of x, and we'll let cosine x be g of x. However, in this second term, we don't have a product. A constant alone is not a product. It's only when a variable is involved that we have to consider it a second function. So for this second term, it's one function, 2 is just the coefficient. So once again, let's just reiterate what the product rule is. Y prime equals the first function times the derivative of the second plus the second function times the derivative of the first. We'll only be using the product rule for this term, and then we'll just take the straight derivative of the second term. So in this case, y prime is going to be the first function, 2x, times the derivative of the second. Remember, the derivative of cosine is negative sine x, plus the second function, which is cosine, times the derivative of the first, which is just 2. Now let's take the derivative of the second term. And since the derivative of sine is cosine, this is going to be minus 2 cosine x. Let's clean this up a little bit. We have negative 2x sine x plus 2 cosine x minus 2 cosine x. So these last two terms cancel, and we're left with negative 2x sine x. It stands to reason that if we needed a product rule for functions that are products, we would need a quotient rule for functions that are quotients, and that's what we have here. The quotient, f over g, of two differentiable functions f and g is itself differentiable at all values of x for which g of x is not equal to 0. This is here because, of course, now we've introduced a denominator, which creates domain issues. This derivative will be defined everywhere on the domain of the function, which, of course, is where g of x is not equal to 0. Moreover, the derivative of f over g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. Here's what this looks like. Let's say your function f of x over g of x is here. We want to take the derivative. Then it's going to work this way. The bottom function times the derivative of the top function f prime of x minus the top function f of x times the derivative of the bottom function g prime of x. And all of this will be over the square of the original denominator, whatever it was. Here we have a quotient, and we are being asked to find the derivative. How coincidental is that? The numerator then is going to be f of x. The denominator is going to be g of x. In a display of mathematical due diligence, let's determine the domain of this function by taking a look at the denominator. As it happens, this denominator will never be 0. So this function is defined on all real numbers. Never a bad idea to take a look at the domain of the function. Now let's recall what the quotient rule is. It's going to be the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, all over the bottom function squared. All right, let's use this rule and take our derivative. Y prime then will be the bottom function, x squared plus 1, times the derivative of the top function, which in this case is 5, minus, don't forget this is minus, in the product rule it's plus, and often that gets confused, minus the top function, 5x minus 2, times the derivative of the bottom function, 2x, over the denominator, g of x squared. X squared plus 1 quantity squared. You do not need to FOIL this out, just leave it like that. However, let's distribute and clean things up a bit in the numerator. We can distribute the 5 here, and we're going to get 5x squared plus 5. Then think of this as a negative 2x being distributed, so we can deal with the negative and the 2x all in one, and that's going to give us a negative 10x squared. And then a negative 2x times negative 2, a positive 4x, over quantity x squared plus 1 squared. And combining the only two like terms we have gives us negative 5x squared plus 4x plus 5 over the quantity x squared plus 1, quantity squared. In this example, we're going to find an equation of the tangent line to the graph of this function at the point negative 1, 1, which is about right here on the graph. As for the domain of this function, we can see that it's undefined at negative 5 and at 0, and there are vertical asymptotes at those locations on the graph. But fortunately, we're being asked to find a derivative at a point that is defined on the function, negative 1. So the derivative that we need will exist here, and we don't need to worry about the places that are undefined in this particular problem. Anytime you're writing an equation of a line, you'll need two things, a point, which we have, and a slope, which we're going to get from taking the derivative of this function. It's definitely a quotient, but since it's a complex fraction, we'll need to simplify it before we can use the quotient rule and get the derivative. So let's rewrite this function, 3 minus 1 over x plus 5. Multiplying it by x over x will deal with the fact that we have a denominator and a fraction in the numerator of our fraction. So let's distribute it to both terms. Our new numerator is 3x minus 1. Distributing the x in the denominator, we end up with a new denominator of x squared plus 5x. Now remember, this is f of x, our original function. It's simplified, and since it's no longer a complex fraction, we'll be able to use the quotient rule and take the derivative. So the derivative will be the bottom function, which is x squared plus 5x, times the derivative of the top function, which will be just 3, minus the top function, 3x minus 1, times the derivative of the bottom function, which is 2x plus 5. All of this will be over the denominator, x squared plus 5x, quantity squared. Now, if the purpose of this problem was to get a simplified form of the derivative, we would distribute, FOIL, simplify the numerator, etc. However, that's not the purpose of this problem. The purpose of this problem is to use the derivative to get a slope at a specific point. So we may just cut to the chase if we want to and plug negative 1 in for x and evaluate the derivative at negative 1 to get the slope there. And that's what I'm going to do. I'm going to find f prime of negative 1. So that's going to give me a negative 1 squared plus 5 times negative 1, all of that times 3, minus 3 times negative 1 minus 1 times 2 times negative 1 plus 5 over, we'll now have negative 1 quantity squared plus 5 times negative 1, and all of that squared. So in the numerator, I have 1 minus 5, which is negative 4, times 3, a negative 12. And then I'm going to have a negative 3 minus 1, which is negative 4. This is a negative 2 plus 5, which is a 3. Negative 4 times 3 is negative 12, but since we're subtracting it, minus a negative 12 becomes plus 12. Now let's look at the denominator, even though we kind of don't need to know what it is, since the numerator is going to be 0, but just to make sure we've done all that we should, negative 1 squared is 1, minus 5, negative 4 quantity squared 16. But of course, the numerator being 0 means the entire value of this fraction is 0. A slope of 0 means we have a horizontal line at this point. We're going to use point slope form. Y minus 1 is equal to the slope 0 times x plus 1. And of course, the equation of the line that we're looking for will be y equals 1. So it'll be a horizontal line at this point. See if I can grab it here. There it is. And there you have it. Not every quotient needs to be differentiated by the quotient rule. Many quotients can be rewritten as constant multiples. These four functions may initially seem as though they are quotients requiring the quotient rule. But when you have a denominator that's a constant or a monomial terms, it is often possible to rewrite the function so that you can use the power rule to differentiate. The power rule is always the simplest, quickest way to take a derivative. So we must become skilled at rewriting functions so that we are able to use the power rule whenever possible. In this first example, since the denominator is just a constant, we can rewrite this using 1/6 as the coefficient of the function. Now the derivative is going to be 1/6 times the derivative of the function, 2x plus 3. The simplified version, y prime is going to be 1/3 x plus 1/2. No need for the quotient rule. Again, since the denominator is just a constant, let's rewrite 5/8 as the coefficient of the function. The derivative then is going to be 5/8 times the derivative of the function, 4x cubed. And when we simplify, that gives us 5/2 x cubed. In this function, I'm going to distribute first, and this will give us negative 9x plus 6x squared. Since the denominator is just a monomial, we can split this into two different fractions. Let's make this negative 9x over 7x plus 6x squared over 7x. We won't worry about the fact that we're continuing into the other columns. Then simplifying each of these fractions gives us negative 9/7 plus 6/7x. That is the simplified form of the original function. Now let's take the derivative. F prime of x, since the derivative of a constant is just 0, this term goes to 0, and the derivative of 6/7x is 6/7. That is your derivative. And in the last example, since the denominator is just a monomial, this can be rewritten as 9/5 x to the negative 2. Taking the derivative then using the power rule gives us negative 18/5 x to the negative 3, rewriting negative 18 over 5x cubed. That's it for today's lecture, boys and girls, and I leave you with these stunning photographs of actual snowflakes, taken with a special camera, of course. But look at the diversity, the precision, the symmetry, the math that is displayed in each of these shapes. This is one of those aspects of nature that points not only to the existence of a creator, but to his incredible mathematical nature as well. Here's a quote by Augustine. "The validity of logical sequences is not a thing devised by men, but is observed and noted by them. It exists eternally in the reason of things and has its origin with God." God bless you, boys and girls.